Today we are starting lecture 34 on optimal generation scheduling. This is different than the earlier one in the sense today we will be considering losses as well. Last lecture of course was unit commitment, and prior to that was again generation scheduling but without losses. And we saw in that lecture that if losses are not there, that means all the units are at the same station. So, no question of any loss. So, how they will share the load? The condition was equal incremental fuel cost. That means dCi by dPgi should be equal to lambda for all I. That was the condition. Now, today if there are different plants located at different places, one is in Haryana, one is in Himachal, one is in UP, one is in Delhi, then there is no way you can assume that there will be no losses, because the power will be travelling over long distances, right. Naturally, anything that travels over long distances is bound to be loss. Even if it is water, there is a seepage loss. This is the oil, there are losses. So, anything. So, PL means transmission loss. This PL stands for transmission loss. Normally in the world, PL is 5 to 15% of total load to be supplied, or total power which is both are same. Ultimately, the load has to be equated to generation. That is a power balance equation. So, this losses cannot be more than 5 to 15% of load or total power generated. But in India, as you know, these losses are very heavy. Even you ignore those thefts etc., even technical losses are very heavy because of bad planning, bad material, everything bad. So, you have to share the losses also while supplying the load. So, that also becomes a part of load, as if you are supplying a load. The losses is gone, I mean that is not serving any useful purpose, however it takes away generation. So, as far as we are concerned, it is a load. Just to give you a technical explanation why we cannot apply the old criterion of equal incremental fuel cost, very simple example I am taking. Generator number 1, generator number 2. Let us assume they are same. By same I mean identical, purchased the same day, same shop, same manufacturing concern, everything same. That means their fuel cost characteristics are also same. That means if there is a load at this bus, this is a generator bus and this is a load bus. If this load is PD, as per our earlier criterion, both the plants or both the units will share half of equal incremental fuel cost. So, they will share half of, but this is a wrong solution. Why it is a wrong solution? This generator has to travel all the way to supply this load, whereas this generator is right close to the load. So, even a normal IQ, I am not talking about high IQ people, normal IQ people or low IQ people will understand it will be wise, it will be prudent to supply more power from G2 rather than G1, because G2 transmission loss is 0, it is right there, and hence G2 should be more than G1 for low losses, less losses, and hence that earlier criterion cannot be applied when losses are to be considered. Then which criterion should be applied? Next question immediately any one of you should ask. Fine, I agree with you that you do not have to apply the old criterion, but then what is the new criterion? The new criterion, to find out, the objective function still remains the same, we are still after the fuel cost minimization. So, the cost function is, or objective function is, minimization of total cost, which consists of summation of all the cost. Summation is on M, M is the total number of plants. This is the equality constraint. Summation of total power generation at m plants minus all load at all the places. N is the load buses, number of load buses, number of nodes, number of points where load is there. It is not necessary to have load at all the buses. Never be under impression that a generator cannot be at all the buses, because it is a costly affair. It is normally 10 to 15% of total buses have generations attached to them. This we have done in our load flow chapter. Minus PL, PL is the losses. This is an additional term which is coming vis-a-vis the last to last lecture. Now this can be rearranged since load is a constant thing. Now here I am assuming that a very big assumption, load is known with complete certainty. I am assuming that the loads are known, that is load forecasting is perfect, and whatever load has been forecasted, the same way load comes. So load is a certain variable, is a certainty, though in practice it is a random variable. All of you must have read stochastic control or control system, probability theory, random variables. Truly speaking, load is a random variable, because even God does not know what will be the load tomorrow, if at all there is any God, right. It varies. You may forecast it with a mean value, with a standard deviation, Gaussian distribution or any other distribution. The beauty of Gaussian or normal distribution is the first two moments describe it completely. I do not know how much your background is of probability theory or that populist book, whether you have read random variables and stochastic processes, etc. There are so many things to learn in life. It is not possible for every one of you to learn everything. So I can lump it to a constant value PD. This is the justification for lumping this summation to a constant value, because they are all known. So now this has become our new load demand equation or equality constraint. So I am now defining Lagrangian. The C upper bar could have also been written as Lagrangian. CIPGI, the original objective function, augmented by lambda times the equality constraints. Luckily there is only one equality constraint here, there is no other inequality constraint. So one equality constraint, that means only one lambda is required. This is what is Cohen-Tucker theorem, which is given in appendix E. So I have requested earlier also to read that. I hope you would have read it, otherwise you should read it. Now this lambda is called, there are several names given to it in literature. It is called Lagrange multipliers, it is called adjoint variables, it is called co-state variable. Control people will know it better, but whatever it is called, it is an unknown. So you have to evaluate it, that is the bottom line. And PL has, this is a new entry to this game. So we just up to this point we could get away with writing PL. Now the time has come when you have to explicitly express PL in terms of control variables. And what are the control variable here? Only one, PGI. Such a beautiful control problem you would have never had, practical problem, where there is only one control variable. This is PGI, that is power generation at a given plant I, or at ith plant, the way you want to write. So the losses have to be a function of generations. If there are no generation, no losses. Losses are there because there is a generation. Water leaks because there is a water in the pipe. If you stop water, as in many colonies there is no water, where is the losses? There are no losses. So losses are there because the original substance is there. Now this function can be evaluated, and in last 50 years people have tried to evaluate in a different way. People have done BTech projects, MTech projects, even PhD. on finding out modeling of these losses and minimizing them. And still work is going on, still people do MTech project, PhD project on loss minimization. But the original formula given by Kirchmeier, who is considered to be the father of economic operation, he has written series of 2 books, 1958 and 1959, published by John Wiley. They are still the Bible. Both of them are available in low price, they are available in library. If you have a time, kindly go through them. Now for optimum real power dispatch, the Cohen-Tucker conditions KT, these are necessary conditions, not sufficient. Those of you who have done optimal control or optimization techniques will know the difference between necessary conditions and sufficient conditions. For example, to pass a course, it is necessary to attend classes. It is not sufficient. Suppose you don't study, you don't go back and work, read book or read notes, you may not pass. So it is only necessary, not sufficient. I'll just to give a practical real life example. To be a Brahmin, it is necessary to be a Hindu, not sufficient. Why? All Hindus are not Brahmins. Reverse may be true, all Brahmins are Hindus, but all Hindu, it is necessary to be a Hindu, to be a Brahmin, but not sufficient. So I hope you have understood the difference between necessary conditions and sufficient conditions. Your earlier teachers in optimal control or in optimization might have explained to you what is necessary condition and what is sufficient conditions. So these Cohen-Tucker conditions are necessary conditions for optima to exist. So for optimal real power dispatch, you differentiate the Lagrangian with respect to control variable. Here is the only one control variable, so I differentiate it. This any BSc student will find out this derivation, or even high school, dCi dPgi minus lambda plus lambda times del PL del PGI is equal to 0 and for all I, right. You simplify, you get this equation, dCi dPgi 1 minus del PL by del PGI is equal to lambda. Anyone or all of you are intelligent, that is my assumption, and I am sure my assumption is not wrong. This is the only term which was not there earlier on. This thing was there earlier. So this is a new term, and this 1 upon this is called Li, penalty factor, PF, not power factor, penalty factor. I can briefly write the numerator as IC, incremental cost of I, into Li. Li is a penalty factor, it should be equal to lambda. So modification is this term, and that is why, since it is exact now, this is called exact coordination equation. So if a question comes, derive exact coordination equation, that means this derivation should come, not the earlier one. All this experience of 35 years of mine suggest 25% students still derive the old one and not this one. So when I ask to derive exact coordination equation, this is this equation which you have to derive, not the earlier one without L. The units of lambda is rupees per megawatt hour. So incremental fuel cost criterion, this new term has come, del PL by del PGI. The people in literature, experts in power systems have called it incremental transmission loss. So if there is a change in a generation by delta PG, what is the corresponding change in loss is called incremental transmission loss. So delta PL upon delta PG. Now we come, the time has come to give you the expression for PR. We have talked about it a little while ago, but we haven't yet advanced any expression. Now I am writing an expression in 3 different forms. The first form is a matrix form. P transpose BP. P is a vector of power generation. If you want, you can even write PG. B is the loss formula coefficient matrix, okay, which is given here in expanded form. PG1 up to PGM, PG1 up to PGM, and this is a quadratic form. Again, in linear algebra, those of you who have studied linear algebra or control system, they know about quadratic form. If you want to write in the index form, two summations I1 to M, J1 to M, PGI, Bij, PGJ. If it is a two plant system, then the answer will be B11 Pg1 whole square twice B12 Pg1 Pg2 plus B22 Pg2 whole square. This will be PL for two plant system. That is expansion of this. If it is 4, if I expand, maybe whole sheet is required to write that particular equation. So, these are the three different ways in which you can write. The derivation of this is given in all the books. I do not think that is necessary to go through that derivation. In fact, Kirchmeier has given chapters just on to derive this particular equation. From there you can understand how important is this equation, that even after 50 years of that first enunciation, people prefer this formula rather than intermediate. Many papers have come, many formulas have come, all have been discarded, and this is the only formula which is most respected, most valued and most used. Substituting various values in that exact coordination equation result, we get this Bi plus 2Ci Pgi, this is dCi by dPgi. If it is a quadratic equation, you get this. By differentiating, you get a linear equation, incremental cost curve, plus lambda times, if you differentiate del PL by del PG, what you will get from quadratic form, 2 times Bij Pgj is equal to lambda. Any difficulty in this equation? Once you get this equation, then since I am interested in find out the value of Pgi, I separate out Pgi from here. So, j not equal to I, rest terms are same. Then I collect all the coefficients of Pgi, which I normally do in deriving anything. Rest of them are in right hand side. So, Pgi becomes this, and this is CTM. CTM is commit to memory. This is the final derivation for Pgi. So, for a given value of lambda, equation A can be solved iteratively by assuming initial values of Pgi. Why you have to assume? Because Pgi is both the places. So, in order to any iterative process, all of you know that you have to initiate the iteration by assuming initial values. If you do not know anything, what you will initiate? Anybody? Say you have no knowledge, what values to assume. So, what is the best value to assume? No, this is not a flat voltage start, that is a voltage 0. Let us assume that there is a zeros in the relation and it will converge. It is like a Gauss Seidel. Once you know the value, start using them. Say you are calculating Pg4. So, up to Pg3 you have a values, do not assume 0 there, because you have just calculated Pg1, Pg2, Pg3. So, use these values while calculating Pg4. P5, 6 etc. you can continue to assume 0, but not prior values, because you have updated values, that you know, of course. That is what is Gauss Seidel. For a given value of demand, naturally you have to have a demand then only you try to find out optimal values of various generations. Solve the equation A by using the following algorithm. Initially choose lambda is equal to lambda 0. Lambda value you have to assume. Assume PGI is equal to 0. This I just now told you. Assume PGI is equal to 0 for all I. Solve equation A iteratively for PGIs. Calculate PL. Now you know the formula for PL. B coefficients will be given to you. If not given, you can compute them. The formula is again given in the book. But as far as we are concerned, you will be given the values of B's as far as this course is concerned, this exam is concerned. Calculate PL, check if power balance equation is satisfied. I told you many times that any optimization technique, three basic things are required. How do you start? How do you proceed? When do you stop? You have to stop somewhere, otherwise you go on and on and on. Even in your exam, you have to stop at 9, at the most you can continue up to. I have seen students even taking 5 minutes out of the exam period, reading something. Sir, अभी हुआ नहीं है, अभी रह गया सर. अभी ये कब तक करते रहोगे? 12 बजे तक ये करते रहोगे, फिर एग्जाम कब दोगे? चलो रखो किताब ना जाओ. The best thing the psychologists say, you must stop reading 1 hour before the exam. Have fresh, maybe watch some TV or some Walkman or chit chat with your real friends, not the other ones who can tell you that you are not going to get good marks today. So those demoralizing factors you should be away. Okay, and then come slowly walk towards exam hall, sit, think some good things in life, and then start. So here the power balance equation is the thing where you can stop, see whether it is satisfied, because the whole thing is done to supply power to a given load. So sigma, absolute value of sigma PGI minus PD minus PL should be less than certain epsilon, which is again fixed by you, depends on what accuracy you want, tends to minus 4, 0.001 or 1, whatever. If yes, stop. Otherwise, OW is otherwise continue. How should you continue? The sixth step is very crucial. Lambda should be now revised. If you recall, the very first step we assume lambda is equal to lambda 0. That means that lambda 0 is not good enough. So add to that by delta lambda if power balance is less than 0. Negative, it means generation is less, load is more. Or if it is otherwise, that is generation is more and demand is less, then subtract lambda and new lambda will be lambda minus delta lambda. Repeat from step 3. Can you give me one caution here? If you are caught, there is one danger in any iterative process. I will explain you again by a real life example. Say you had to go to Mehroli, that is Qutub Minar, you are starting from Ames. Okay. Now, if you are proceeding towards your objective, that is Qutub Minar. Say you come up to IIT, you check, is it Qutub Minar, you stop your car and ask somebody, bhai ye Qutub Minar hai? दिखता नहीं है किधर है मीनार इधर, this is IIT. Oh, IIT, then what should I do? Go ahead. And suppose he goes with that step size that he reaches DLF. You know DLF quarters are there in Gurgaon. He has left Qutub Minar far behind. Then he asks, भाई किधर है? ओ भाई बहुत पीछे छोड़ा है तुम, वापस जाओ पीछे. अच्छा ठीक है. Suppose he again comes to IIT. What is this process? This is called oscillation. You are oscillating around the solution, which is the most dangerous thing that can happen in any iterative solution, because then there is no solution. Then you keep on going DLF and IIT, DLF and IIT and never reach manually. So what should you do? Next time if you have to add and subtract, don't do by delta lambda. Otherwise, what will happen? You are back to the same lambda. So your program should take care of this delta lambda by 2. Progressively reduce or increase the step size. If you keep the delta lambda same, then one way you are adding delta lambda, next time you are reducing delta lambda. That means you are still at lambda. You are still at IIT. You are not reaching Qutub Minar. This is the moral of the story. So the teacher might have taught something. This should come from your general knowledge, your IQ. Example 7.4 and 7.5 from this book, or 7.5 and 7.6 from other book, that power system engineering. These are two good examples. You should try to solve them. They are already solved. And how do you solve the solved example? By closing the book, just note down the problem and try to solve it. The advantage is you will come to know where you have gone wrong. In other unsolved problems, if you don't get the answer, then you don't know where you have gone wrong. Then if your friends solve independently, then it can perhaps help, provided you are not making the same mistake. Again there will be a problem if you are making the same mistake. You may say the book is wrong and we are right, whatever answer I am getting. Sometimes it may be right, your book may be wrong. After all, gods have not written books, some human beings have written books. And then there are some proofreaders, and then there are some illiterate people who are doing this job. Now we come to the next article, optimal load flow solution. We have done load flow, but we have not done optimal load flow. So far whatever we have done, we are solving the network assuming the losses. But some purist may say this is no good. Losses is after all an approximate way of assuming by a formula, B coefficient formula. Some people call it B constants also, but remember they are not truly constant. They vary with operating conditions. So you may have to use a set of B coefficients and they may be re-evaluated once there is a good change in the operating conditions. I don't want to use the word drastic. If there is a drastic change, naturally you have to change them. So optimal load flow solution is one where the load flow solution is optimal from some point of view, some criterion of goodness. Now let us do without inequality constraints to keep our life simple. We will consider inequality constraint later on if time permits. Again the objective function remains the same. C is equal to sigma I Ci Pgi, subject to SLFE, static load flow equations. You know load flow equations. Pi Qi is equal to, you have done it in last chapter. Incidentally, in exam we will have both the chapters, chapter 6 and 7, and you will get paper from my portion of 13 marks, 1/3 as usual, because the total paper will be of 40 marks. Either there will be one big question of 13 marks or there will be two small 6 and 7 marks. Alright, and you should prepare examples, you should prepare some derivation and some small questions as I normally ask. Why do you want slack bus? What is the significance of slack bus? What are the conditions for a bus to be eligible to become a slack bus? Like that. So that just to test your concept and understanding of the course. Fxy, that is a function of x and y. What is x and what is y? X is a state variables, y is a control variable, or at least y contains control variable. Subset of y is a u. X is also called dependent variables or state variables. Y is called control variables or independent variables. I think independent variable is a better term, because y is only the subset of y is only u. The whole y is not a control variable. You can have it as a control variable, but cost. You can't control everybody. Where the vector of dependent variable is, let us find out what is x. So, fxy is pi qi for each PV bus, sorry PQ bus, and only pi for PV bus. Okay, because qi is not known. So, there is no point in writing equation for qi, whereas for a PQ bus both p's and q's are known. So, what is x? X is Vi magnitude and delta I for each PQ bus. What is not known is dependent. They are dependent on what? What is known. Everything is follows from real life. And delta I is not known on PV bus, because voltage magnitude is known. So, I can't write that here as a something which is unknown, something which is dependent. Similarly, vector of independent variables is y. So, slack bus V1 and delta 1 are known. So, they are independent. Similarly, Pi Qi are known at each PQ bus. So, they are independent variables. Similarly, Pi and Vi are known on each PV bus. So, that is again part of y. As I told you little while ago that y, the whole y should not be considered as control variables for two reasons. A, there is no need. B, involves cost. Anything which you want to control involves cost. It is like in a locality, if you are a superintendent of police, if you keep watch on only gundas, that is enough. Those who are law abiding citizens sleeping in their houses, why should you stand and go and whole night there? They are sleeping. Those who are on the road, those who are moving in their cars, going for bar or restaurant or whatever, you have to keep watch on them, that is all, and there will be law and order. That is why only a portion of y should be considered as u, rest will be called p. Now, what is p? P can be, truly speaking, variables which need not be controlled, as I said, or they are disturbances where control is not possible or tough, involves more money. So, P in literature is called either the constant. Constant means you can't control, you can't change its value. Control means you can change its value, change its behavior. Objective function must include Pg1. Why? Suppose you do not include Pg1 in this objective function, C is equal to sigma Ci Pgi, what will happen? It is a slack power, Pg1 is a slack power. If you do not include that slack power, so many questions, people ask questions, why should we include slack power as a control variable? If you do not include, what will happen? The optimization process will try to allocate maximum power to the slack, because you are not paying for it as if it is free, which will be wrong, because here also you need coal, here also you need oil to produce power. So, Pg1 must be included in objective function. Oh, here is the definition of P, which I have already told. Pi is fixed, uncontrollable or disturbance variables. I told you all the three. Some examples of control variables out of y, which will be called u. What are they? Voltage. You can control voltage, you can vary voltage by various means, by excitation, by taps, by SVS, by facts. You had a good dose of facts on those last weekend. This gentleman, 850 rupees. And PGI, power generation is controllable. by controlling the steam. You must have had a heavy dose of AGC when Dr. Bhatti is teaching. AGC won't be far behind. So, AGC means you have to have a steam input can be controlled, or water gate opening can be controlled. So, PGI can be a control candidate for control variable. Tap setting. Tap setting is also a candidate for control variable. Either the what you call on load tap changing or phase shifting, which can control eventually the power, real power, and these taps will change the voltage, and so reactive power will be changed. That is QGI, that is again a control variable. The capacitor, the value of capacitor, the location of capacitor, each changes the scenario in the power system. This itself is a very important topic in power system, location of capacitors. Where do you want to locate FACTS devices, UPFC, SVS, and there are so many family members of FACTS. There are books written on FACTS. You must read them if you want to go into some power business like NTPC, Power Grid, BHEL, CA, or abroad power technologies, and EPRI, Electric Power Research Institute in US, very good. There are so many good Indians there. Keep track of papers coming in the transactions, write to them that I am doing. They need cheap labor, pardon my saying that, because Indians are, for them it is a cheap labor. So, you can go abroad if you want to after your MTech. Right. Suppose I am interested only in minimization of real power loss, because that it's too much in India, I told you. So, my objective function now becomes not the cost, but slack power generation, because it is a slack power generation which satisfies or which supplies majority of transmission losses. So, this problem is called optimal reactive power problem, reactive power minimization problem, and this has been dealt in a paper by Domel and Tinney. This is a landmark paper, milestone. This paper must be read by you, 1968 IEEE transactions on power approaches and system. Hopefully its page number is also 1968 if I recall properly. I may be wrong, because 68 is already more than what, about 38 years, 37 years back. 2005 is around the corner. But in case you are doing a project in this, then you must read this paper. Have you finalized your projects? Minor project, major projects? Not yet? Again, the objective function is minimization of C of xu. Now, this is a vector. Subject to equality constraint. Equality constraints are those two load flow equations, SLFE, f of x of u of p. I have removed y and put u and p equal to 0. That is your equality constraint. Inequality we have already ignored. We are going to consider it next time, time permitting, because I also want to do hydrothermal. Maybe we will do in that power system analysis course. In that also I will have 1 hour only. Balu will take 2 hours, I will take 1 hour in the evening. Now, this lambda is no longer a variable, Lagrange variable or co-state variable or adjoint variable. Now, what it is? It is a vector of Lagrange multipliers. As many load flow equations, as many lambdas. That is why I have written lambda transpose. You can't multiply two vectors just like that. They may not be compatible. So, the number of rows and number of columns should be equal. All of you know better than me the rules of vector algebra or matrix theory. And again Cohen-Tucker conditions will come into play. They are necessary conditions. And what are the Cohen-Tucker conditions? Del Lagrangian by all the three variables should be 0. It is no longer only control variable. Delta L by delta x should be 0, delta L by delta u should be 0, delta L, L means Lagrange. I am not, don't want to say Lagrange, so I am saying L by p should be 0. I am giving here the expanded version of delta Lagrange by delta x, del c by del x plus del f by del x transpose into lambda is equal to 0, del L by del u is equal to delta c by del u plus delta f by del u transpose into lambda is equal to 0. The encircled components of these equations are very involved. Computation of these two components, the computation of these is very involved, and a Domelantini book has, not book, paper has spent one full page on each. So, in case you are interested, in case you get enthused to find out why they are involved, please read that original paper, provided you get in the library, because in olden days when we used to give such references, our students who must be now in their 50s, they used to tear those pages. So, the first person who runs after the class, who is smart and lean and thin, not like me who cannot run, he used to do this job, which is very bad. So, do not think the bad habits have come now only, they are there since time immemorial. And so, journal may be there, but that paper will not be there. So, do not blame me if that paper is not there. Maybe now internet is there, so you can download it, and that is a good thing that internet has done. The bad thing is it has started producing reports, MTech thesis, PhD thesis by downloading. So, you do not understand what is there in the thesis because you have downloaded it, you have not worked yourself anyway. So, del f by del u is equally involved, but this particular fellow is nothing but our old friend Jacobian. Jacobian you know how to evaluate because you have done it in load flow chapter. This is J, del f by del x is nothing but Jacobian, that you know. This is very simple to evaluate, we have already done it, del c by del pgi. Luckily the third equation results the same good old friend, the load flow equations, fx u plus p is equal to 0, that you can immediately recognize as your equality constraint. So, it does not give any extra new information, it is an old thing. Non-linear, these all three are non-linear algebraic equation. Luckily there is no time involved here like stability, no differential equations. So, but again there is a iterative solution is required because they are non-linear, highly non-linear. We, since it is an optimization, is no longer a plain load flow, so we need to have an optimization technique. An optimization technique which we use here is simplest possible, called gradient method or steepest descent method. Again you have to adjust initial u, you have to assume, and then adjust u to move from one feasible solution to another. So, as long as that fellow is coming from Green Park to Hotchkiss to IIT and then Qutub Minar, he is converging. So, step size is very important in optimization, the correct direction is very important in optimization. So, but feasible solution should also be there, otherwise if you are going into infeasibility you cannot achieve optimality. Even if you achieve optimality, it is of no good. Any optimal solution by which I can't satisfy my load is not optimal, it can be anything but optimal. Repeat till minimum is achieved, this is true in any optimization process. Let us consider the algorithm. Assume initial value of control vector. Find feasible load flow solution by Newton-Raphson method. XR plus 1 is equal to XR plus delta X. This is nothing but a load flow solution. The end result is feasible load flow solution, that means you get the value of X and value of J. X is a dependent variable and J is a Jacobian, which you get in load flow solution. This whole step is nothing but load flow solution. Find out lambda from one of those equations. this equation and this equation. Lambda converts, send this right hand side, so minus sign will come, take invert of this and multiply it, you get lambda. Is it alright? From here you get this. Insert lambda in second equation. Third equation is no use, it gives me same good old equality constant. So from first equation you find out lambda, substitute into second equation to get gradient, because the second equation is nothing but a gradient. What is gradient? First order derivative of what? Lagrangian with respect to control variable. So del this is like your field theory. I don't know how many of you have read Maxwell's equation, divergence D is equal to 0, curl and all those things. So this is that del. So del Lagrangian nothing but del C by del U plus del F by del U transpose into lambda. And if this gradient is 0 or nearly 0 within certain tolerance epsilon, then minimum is achieved. Otherwise, find a new set of control variables and repeat. How do you find out new set of control variables? U new is equal to U old plus delta U. You have to add something to the old to get the new, or subtract, one of the two things, like we did with the lambda if you recall, where del U is minus alpha times gradient. What is alpha? Alpha is a positive scalar. Why minus? It is called steepest descent technique, because we are going for minima. If it is maxima, then steepest ascent technique. If you have to go to Himalaya, there is an optimum path, which your Sherpas will tell you or your trainers will tell you. To reach Himalaya is your objective. How do you reach? With minimum efforts and minimum time. Now sometimes time is not important, then take a longer route, but with efforts less. It all depends on what do you want. So delta U is a step in negative direction of gradient. Alpha, by varying alpha you can vary this step. So what is the critical step? What should be alpha? Ultimately problem is postponed to deciding what should be your step size. Should you ask gentlemen every 5 minutes, bhai Qutub Minar aa gaya kya? Or you should stop only once somewhere in between, but that one should not be DLF quarters. That is the real challenge, in that comes by experience. If alpha is too low, convergence is slow. Suppose you start asking every feet, पागल हो गया, अभी पूछ रहा था, फिर पूछने लग गया. But convergence is guaranteed, you will reach Qutub Minar. However, if you ask alpha take a long step size oscillations, DLF. So then what is the real thing? Well, there are again optimization techniques available to find out alpha. I don't think we should go into that, but the references are given in the literature, and lot of people have worked to find out what should be the optimum size of this, what should be the optimum value of this alpha. Well gentlemen, today we have finished without inequality constraint. We will continue this problem with inequality constraints, and inequality constraints are there on X as well as on U, both to be treated in different way. And then hydrothermal scheduling will be our last section in this particular chapter. Thank you.